This is a nautilus, a primitive mollusk that uses its shell to keep it buoyant. The nautilus has survived in a form that's been relatively unchanged for over 500 million years. It builds a shell up to 30 centimeters in diameter, which is a triumph of natural engineering and geometry. This cross-section shows how the shell is made up of chambers, each of the same basic shape, but built progressively larger as the nautilus grows. The chambers are filled with gas and liquid, which it can control to keep it buoyant. The geometry of the nautilus shell can be expressed mathematically by saying that each chamber is related to the next by the same rotation and scaling relative to the center of the shell. In this case, the rotation angle is about pi/8 radians, and the scale factor is about 1.06, with only small variations from chamber to chamber. This repeated rotation and scaling gives the nautilus a spiral shell. It's approximately an equiangular spiral. Human designers often take their inspiration from nature, and designs based on spirals are common. A colleague showed me a very nice spiral you can make using rotations and scalings. The idea is to start by drawing a square, and on top of that you draw a right angle triangle, which is isosceles. So this angle is pi/4. And that's the basic shape, the basic figure. Next you draw exactly the same shape but scaled down by a factor on this side of the triangle. So there's a square, and then that's followed by a right angle triangle. Now you can see that this second shape is scaled down by a factor which is in fact 1/√2. If that's 1, then that's 1/√2. And then you repeat the process. On this side you draw a square and a right angle triangle, and then a square and a right angle triangle. You can see that this will produce a spiral, but it's not clear immediately what the center of the spiral will be. But if you investigate it, you find that the center of the spiral is going to be the point that you obtain by drawing these lines. So the spiral is obtained by taking a basic figure and repeatedly rotating it through pi/4 about this point and scaling down by a factor 1/√2. Well, you can get a much more accurate picture of what happens in the long term by using MathCAD. Well, here's a MathCAD document that draws that spiral. We've built it up in stages. First we define the rotation angle, that's theta, pi/4, 45 degrees, and the scale factor, which is a equals 1/√2, about 0.7. Next, we define the rotation matrix in the usual way, r of theta, and a uniform scaling matrix, u of a, defined like that. Now if we multiply u of a and r of theta together, this gives us a matrix A, which has those entries, and that matrix will perform both the rotation and the scaling together. The next thing you have to do is to define the vertices of the basic figure. The vertices are defined as vectors, columns, and the first few of these define the vertices of the square, and the last few define the vertices of the triangle on top of the square. And if you plot the basic figure, this is what you get. And if we want to plot the successive images of that basic figure, we're going to have to multiply the coordinates of the vertices by powers of a squared, a cubed, and so on. And that's what happens here. So if we change to 1, we get 1 more. And each time we increase capital N, we get 1 further successive image. By the time you've plotted 8 of those, you can see that the spiral has performed a complete turn around the center, which is the origin. Well, if you look at the space that's within this spiral, then it turns out that you can fit in several copies of the original spiral into that space. And we've done that in another MathCAD document. So in this document, we're plotting essentially exactly the same spiral, but instead of having one basic figure to start with, we have 4 of them. 1 blue, 1 magenta, 1 black, and 1 red. And we've plotted 20 iterates of each of these 4 basic shapes. And you can see that if you follow the blue spiral round, then after 8 iterates, it exactly fits inside the beginning of the red spiral. So these 4 spirals will in fact cover the plane if you extend them forwards and backwards. That is, they tessellate. Now you can see that more clearly by zooming in on the diagram by changing the scale. Here I'm changing it from 2 to 1/8. It appears to be filling in the plane, and that the diagram is symmetric. In fact, it's very striking. If you wanted to use the design, you could copy it out of MathCAD and put it into a paint package. Now, if I want to, I can colour that in very many ways, using flood fill. For example, you could pick this green colour and fill that square with it. And you might fill other squares with the same colour. You might try orange. Well, there are endless possibilities for such colour schemes, and this design may even be of interest commercially. For example, carpet designers need patterns that fill the plane. Brinton's is one of the UK's major designers and manufacturers of high-quality carpets and rugs. The designers at Brinton's use computers to help create the repeating patterns they need. So how does this software help you to design carpets?
It enables me to take out elements from the original design.
Yeah. So that spiral with the tail.
And then to reverse it, to rotate it.
It's rotating through 90 degrees.
Through 90 degrees. If, for instance, it was to be a set angle, that's a little bit more complicated. It's rotated.
I see, so it's rotating down there at the bottom.
Chosen angle. I'm able to select elements from the design.
So you've taken just part of the spiral there?
Just part of the spiral.
And you can scale it. Yes.
Reduce it.
And make it any size you want. So what kinds of carpet designs have you come up with?
From this particular rug design, I've taken elements from there and created a repeating pattern. Opened up the ground, scaled down the design.
So are all those elements from the original rug?
From the original rug, yes.
So you simply rotated them, or...?
Rotated them and edited them so it wasn't so obvious that they'd just taken them and changed them a bit so it wasn't so obvious.
So what would happen if you, for example, took one of those elements and scaled that now?
As the design is set and repeat.
I see, so if you change one, they all change?
They all change, yeah. I'm sure I'm able to see what happens overall.
So this way you can make a full carpet design?
That's correct. By taking the elements from the original rug design, scaling them, rotating them, and to create a repeating pattern for an Axminster carpet.
Our geometric spiral design created some excitement in the studio. One designer spotted another way to put it together. And the way we made it was to start with a square and then build a triangle onto that, and then a smaller square and then a triangle, and carry on going round to produce a spiral design. And that's the way we made it. But when you saw this, you looked at it a different way.
I did. I would start with this one triangle here and first of all put all the squares in and take it from there. And once I've got the squares in, the next thing I'll do would be put the triangles to the side.
So you put a diagonal in then?
Now the next thing I can do is rotate that to build up the next square.
So you're using this whole part of the diagram to...
Yes.
So you've got two triangles now.
And now, just to make the top, I can pivot it round.
Oh. So you've got half the design now.
Got half the design, I just need to do this other triangle. The next stage is to rotate it 45 degrees and to scale it.
Right, and you'll have to scale it by a factor of √2 because that's the ratio of the length of the diagonal to the side of the square.
Yes. So we're going to copy rotate it, pick this one triangle up, rotate it 45 degrees,
And there
and
it
place
is.
it down. And now it's at the wrong scale. And I have to scale it. Copy proportional.
Oh. So that's scaled down by a factor of √2. And that fits. Beautiful.
Right, and I'll just chop it back down to one repeat. And fill this square.
That would have been half of a blue square there, yeah?
Yes. I can just rotate this whole square 90 degrees. And now I can pivot the whole design.
You've got half that, and there's the whole design.
And there's the whole design.
So that's the finished pattern.
It is an effect, but I need to recolour it to get the full spiral effect.
So that colour scheme emphasises the spirals that we started with.
It does indeed, yes.
But what would this look like in reality? Well, Brintons can get weaving on a small scale at this point and create a real sample. So here's the carpet, and the colours have been chosen to emphasise its spiral nature. A spiral constructed by repeated scaling and rotation, just like the Nautilus. And if seeing a sample is not enough, then you can visualise what the design might look like in a room. And if that creates enough interest, you can even go into full production to create the real thing. So, rotations and scalings can be used to produce spirals, whether in nature, as with the Nautilus, or in mathematical design.